Strong bases are all hydroxides of group 1A and calcium, strontium, and barium of group 2A. So if you don't have hydroxide, it's not going to be a strong base. So if we're calculating the pH of a 5 times 10 to the negative second sodium hydroxide solution, first you should write the dissociation equation. NaOH is a base, and it would break apart into sodium and hydroxide ions. Since my sodium hydroxide is 5.0 times 10 to the negative second molarity, that's also going to be my concentration of sodium and my concentration of hydroxide. But if I'm calculating pH, the only one that I care about is my hydroxide ion concentration. You can solve it one of two ways. You can either use the POH is equal to negative log of OH concentration and find my POH, or you can use the H times OH equals 1 times 10 to the negative 14th and find H, and then find pH. If I go with the top route after this equation, I would use pH plus POH equals 14. While if I go the bottom route, then I would do pH is equal to negative log of my H concentration. I'm going to go the top route and find my POH. So POH is equal to the negative log of 5 times 10 to the negative 2. Plugging that in, I get that my POH is 1.3. Therefore, 14 minus 1.3 is equal to my pH. So pH is 12.7. Go ahead and pause the video and try this one on your own. Restart when you have an answer. So this is a strong base, therefore this is my concentration of OH because KOH only has one hydroxide. Therefore, I'm going to find my POH. And that's negative 0.47. This problem only wanted the POH, so I do not subtract from 14. But if it wanted pH, then I would do 14 minus negative 0.47, which would give me a pH of 14.47. Because this is an extremely concentrated solution, as in over 1 molarity, my POH is negative and my pH is above 14. Go ahead and pause the video and try this one on your own. Restart when you have an answer. So this is a strong base. It only has one hydroxide, so this is your hydroxide ion concentration. Since you're looking for the H concentration, the easiest way to accomplish this would have been to use this equation. You could have done your POH and then pH and then found your H, but that would have taken you 3 steps versus just 1 step. But you still should have gotten the same answer. Plugging in our OH of 0.5 and solving for X, you should have gotten your H concentration to be 2 times 10 to the negative 14. Go ahead and pause the video and try this one on your own. Restart when you have an answer. So on this one, this is a strong base, but be careful of those group 2A hydroxides because this produces twice the amount of hydroxide as KOH would have. If we write our dissociation equation, we can see that we had 5 molarity. This one will be 5 molarity, but we have twice the amount of hydroxide, so we have 10 molarity. So my POH is equal to negative log of 10, which would be negative 1. On this problem, we have NH3. We know that NH3 must be a weak base because, one, it's not one of the strong bases that you should have memorized, and they gave you a Kb. If a substance has a Kb, then it's going to be a base because that's the equilibrium constant for bases. So since it's a weak base, we need to find out how much of that NH3 is going to dissociate. So when you have a weak base, you're going to start with the weak base, and we have to do our Rice table. So first step is to write our reaction. NH3 is going to react with water. And in this equation, NH3 is our base, which means H2O is our acid. Remember from our basics, we said that bases are going to be proton acceptors. So NH3 is going to accept a hydrogen from H2O, which is the acid or the proton donor. When NH3 gains a proton, it turns into NH4 plus 1, or ammonium ion. The other product would be H2O losing a hydrogen, turns into hydroxide. You notice NH3, its conjugate is NH4, which is the conjugate acid. And H2O's conjugate is hydroxide, and that's the conjugate base. So notice we just transferred a hydrogen. The base is always going to gain one proton. And we have to put water in this equation because the base has to gain a proton from somewhere. Now we can go ahead and start with our initial. So we have 15 molarity. We need the water to write our equation, but water's a liquid, so that does not go in the Rice table. We have 0 and 0. It's going to break apart some amount. And my NH4 and my hydroxide will go up by some amount. So at equilibrium, I should have 15 minus X, X, and X. My Kb expression. Remember, always write your expression, even if it doesn't ask for it. Would be so. And then plugging in my values. They gave me the Kb. Just like our weak acids, our weak bases are going to be very dilute. So we can ignore that minus X because they're not going to break apart very much. So multiplying by 15 and square rooting that, we get X. And remember, make sure you're defining X. Since we're trying to find pH, we care about the OH, which is X. So X is equal to my OH concentration, and that's 0.164 molarity. But I want the pH. So first, I'm going to find my POH by negative logging that, and I get 1.78. Therefore, my pH plus POH equals 14, so my pH is 12.22. So these are just like weak acid problems, except you have to have water in your equation, so the base has something to gain a proton from. And when you get X, that's going to be your hydroxide. So first you find POH, and then you find pH. So in this problem, we are calculating the pH of a 1 molarity solution of methylamine. I didn't give you the formula of methylamine, so if you get stuck on a worksheet and you're like, ooh, I don't know what methylamine is. Well, HA is the general formula for any weak acid. So when that loses a hydrogen, it turns into A negative. You could use A negative as the general formula for any weak base. So we could just say A negative plus water is going to react to give me HA and hydroxide. And then go on at that point. So you should not skip a problem or not do it just because you don't know what the formula of the weak base is. You can either Google it, or you could just use the general formula. Methylamine, though, is CH3NH2. So we need our water. Our weak base should be gaining a proton, and when it gains a proton, it's going to stick it on the end of that to turn it into NH3. We gained a proton, so that's going to become positive because it was neutral. And we're going to have hydroxide. So I'm going to pause the video and set up your rice chart and solve for your pH. Restart when you have your pH. So make sure that you had your Kb expression. Plugging that in, we can ignore the minus X, and we get our concentration of OH to be 0.0209. If you're ever in doubt on if you could actually eliminate that minus X, remember you can calculate the percent dissociation. If it's less than 5%, then you're good. So if I was to calculate my percent dissociation, remember it's X, which in this case is 0.0209, over my initial concentration, which was in this case 1 molarity, and then times 100. Solving that out, I get 2.09% dissociation, which is less than 5%, so I was correct in being able to eliminate that minus X. So my X was 0.0209. So to find my POH, I negative logged it. And to find pH, I'm going to do 14 minus my POH, giving me 12.32. I'm going to pause the video and try this one on your own. Restart when you get an answer. So you should have gotten 2.8. If you did, you can fast forward to the next problem. If you didn't, then go ahead and pause the video and look at the work. So that's the work you should have had. We calculated our X to be 0.00158, and then negative logging that, you get 2.8. Make sure you read carefully. This one asks for what is the POH, not the pH. I'm going to pause this one and try this last one on your own. Restart when you have an answer. You should have gotten 10.04. If you did, then you are good and you can shut off the video. If not, go ahead and pause the video for the work when that pops up in just a second. So here's the work on how to get that. Notice they didn't tell you the formula of the weak base. So in this case, you had to use the A negative plus water yields HA plus hydroxide. Solving for X, that's still our hydroxide ion concentration. And if you found your percent dissociation, although this was a very dilute acid, or very dilute base to begin with, our hydroxide ion concentration is still less than 5% dissociation. So finding our POH, we negative log our hydroxide, and then 14 minus that gives us our pH.